It is week 4. It's week 4, guys. You've made it. You have made it this far. Congrats. It's lab 3, part 2. Now I know it doesn't make any sense, but that's what it's gonna be. Basically, it's just more on acceleration, but this time we're focusing on free fall acceleration. This week's theme is also New Girl. If you haven't seen it already, go watch it. It's a great show. It's so funny. I've watched it since I was in high school. So, yeah. Okay. First thing, free fall acceleration. So what is free fall acceleration? Can somebody tell me what that is? What is another word for free fall acceleration?
I guess 9.89 would be the acceleration of gravity. So that would be
9.89?
Is it 9 or 9.69 or 9.
Okay, so it kind of all depends on where you are in the world.
Yeah.
We'll get to that. We will get to that. So you did say gravity, and gravity was the word I was looking for. Let me see if this chat box opens, and it's not opening, so, okay. Whatever. Okay, free fall acceleration is called gravity, basically just gravity. We're gonna go ahead and watch a quick video on gravity, and you're going to make a guess, sort of, even though there's a picture already right here. If I drop, let's say, a rock about this big, and I drop a feather, what's gonna hit the ground first if I dropped it from, let's say, 6 feet? Type it in chat when chat works. I don't know where it went. The chat box is nowhere to be found. Oh, there it is. No one knows what hits the ground first. Nobody? Nobody knows. A rock or a feather? Oh my goodness gracious. Okay, all right, good. All right, sorry. My chat was being super stupid. Okay, I see you've already answered. Yes, it is a rock. It's a rock, of course. Now, in a vacuum, it's different. And when I say in a vacuum, I don't mean the vacuum that you use to clean your floors or your couch or whatever you do to clean your house. I don't know. I'm not talking about that. Same sort of type of mechanism, maybe a little, but we're talking about a vacuum. Is there a vacuum? Is there anywhere in this universe where there is a vacuum, like a naturally occurring vacuum? Naturally occurring. Do you know? The chat box went away again. This is so stupid. Okay, I don't know why. One sec. I have to fix this. I have to. Two people said space. You're right, it's space. There's a naturally occurring vacuum in space. This is what, when astronauts get launched into space and they're going to the International Space Station, they're experiencing, when they get to, of course, into space, above our atmosphere, in the International Space Station, they don't sit there and walk around, you know, this isn't Star Trek. They're floating. They're in a vacuum. They're experiencing what? What are they experiencing? They're in free fall. Yes, yes, they're in free fall. They are, yes, that's what that is. Yeah, because they're orbiting around the Earth, so they're going like so fast. They're just like, woo. Yeah, basically how it works. We're gonna watch a really quick video about items falling in a vacuum. And this just decided to not go full screen. There we go. What is this nonsense? What is this? What are we experiencing here? Oh, okay. I guess we've switched. Okay. Yeah, this is what's happening. If you wanted to do this experiment, there is a hard way to do it. It's probably just as expensive as that place you just saw. Now this place where they dropped the bowling ball and they dropped the feathers, this occurred in a lab. I think it occurred in England. I think there's a lab in England where this happened. Hence BBC's recording production on it. That was an expensive facility to build. Also an expensive thing to do is like launch yourself into space. You can also do this on the moon, sort of. It's not as effective, I would say, because the moon still has its own gravity. So it's a little, you know, but basically if you were to go, the hammer and the feather would fall at the same time. The heavier item, it doesn't matter about mass. Mass has nothing to do with why these objects fall. It's all about the force of gravity. Very, very cool thing. So this is like the first force we'll get into. All right, here's this weird looking person, witch, sick looking person here, I don't know. And they decide to drop some random thing off a cliff, which I can only think of as a witch. It's also going to be October next month. So I just imagined a witch. Yay. Anyway, yes, so you can see she drops it. After 1 second, it goes right here. But after 2 seconds and 3 seconds, look at that. How does that make sense? Why at 5 seconds is it so much further down than at, let's say, 1 second? Yeah. Yes. Yes, gravity. So, objects, like let's say this bowling ball that she has, I don't know, rock, something, let's just say it's a bowling ball. She has a small bowling ball in her hand. This object is technically in free fall. And for this part of the class, we're going to say that this object experiences no air resistance. So there is no air, like there's no force slowing down this object because of air resistance. This is, we could say, in a vacuum maybe. And all objects free fall at the same rate of acceleration. Doesn't matter how much they weigh. It doesn't matter how much stuff makes up that object. So if you dropped an elephant and you dropped a feather from the same distance, let's say a height of 30 meters, what do you think would, which do you think would hit the ground first? I'm gonna get my tea. You would think the elephant. You would. And in reality, yes, for sure, definitely, that elephant would fall and smack right there. Now, let's just say it hit a trampoline so it doesn't, we're not like abusing these animals. That would be terrible. Like, please don't do that. Don't try this at home. Don't do this to your dog. Like, please don't do it. So let's just say he fell onto like a huge pillow. he still reaches the surface of the ground faster than a feather in the air on Earth. But in a vacuum, so let's say the same vacuum chamber that we saw in the video, would they fall and hit the ground at the same time? Would they fall and hit the ground? Would the feather hit first? Would the elephant hit first? This is in vacuum. Type in your answer or say your answer. It's okay. Yes. Oh no, said same time. Lauren, same time. Yep. Yes, exactly, guys. Exactly. Awesome. Perfect. You get this. This is easy stuff. You got it. You got it. It's really cool. You have to just delineate between a vacuum and real life. So you have to make sure when you go do your homework that you're really reading those questions carefully. I know I didn't write the questions, nor did Dr. Diamond, but they may try to trip you up. So just make sure you have your eyeballs peeled for some confusing words. Okay, free fall acceleration. We're gonna go look at the Phi-Fox version or experiment for free fall. Now they're doing theirs a little differently than what it says in the lab, and that's okay, that's fine. If you would like to be super creative, you can do whatever you want. If you decide that you see something on Phi-Fox and you think it would be more fun or cooler, then you go do that to measure what we're doing for the lab. It's up to you. You know, if you're still kind of unsure about Phi-Fox, I would just go ahead and stick with the lab. But if you're feeling confident, you can do whatever you want. So we're gonna go ahead and watch this video before we get into all the nitty-gritty stuff.
Hey folks, this is Sebastian, and today I'm going to show you how to measure the duration of a free fall using your smartphone.
Can you guys hear it? Okay.
A while ago, I posted a video in which I demonstrated how to measure the speed of sound using your smartphone. If you missed it, check it out in the description, it's quite nice. And today we're going to use the same tool, the acoustic stopwatch. If you did not already install our app, get it for free on Android and iOS from phifox.org. In the main menu, you will find the experiment acoustic stopwatch. When you start with the play button, it simply counts the time between two loud acoustic events. The threshold sets the volume at which it reacts. If it is too sensitive and starts because of background noise, increase the threshold. If it misses events, decrease
This is
the
just the sensors. So he's setting the sensors
any noise
to like super sensitive or not sensitive. You might have to adjust
it. Can also be above the threshold. You can adjust a minimum delay to prevent a single sound event from triggering the stopwatch multiple times. If your sound events start the stopwatch but also stop it right away, you should increase this value, but it should always be smaller than the time you want to measure. So what we want to do now is we want to drop some object and measure the time it takes from its release until the impact on the ground. To do this, we need two triggers, two sound events which indicate that the drop started and that the drop ended with the impact. With that, we can then use the acoustic stopwatch to measure the time. So let's start with a very simple setup that you can try out at home. For this simple version of the experiment, you will need three items: an object you want to drop, a ruler, and a pen or similar long object. Now place the object on the ruler, so you can hit the ruler from underneath the object. You should hit it in a way so that the object...
So did you hear that? Did you hear that it made a sound when the pen struck the ruler? And then it made a sound when that marble hit the floor. So that's what this acoustic stopwatch is measuring. It's only measuring sound. It's not measuring it's not measuring the odd, it's just measuring the time it takes from the first sound to the last sound, and then it'll stop automatically. You don't have to, now you have to click, of course, play, and then it'll wait for the sound, and then it'll wait for the second sound, and then it'll stop automatically. Very cool.
Object simply starts to drop without being accelerated vertically by the hit. The idea is that the hit makes a noise which starts the stopwatch, and the impact on the floor makes a second noise which stops the stopwatch again. So this setup was really simple and you can just do it at home. Only problem with this is that it's a little bit too quiet. So if you want to try it in a classroom or in front of an audience or
if you have a loud house,
you need
your siblings
a louder
scream,
trigger sound.
you might
So
want
for
to do
example, what
another
we do
version.
Now is we start the fall by popping a balloon. And again, the stopping sound will be the impact on the ground, but with a nice metal plate, it becomes much louder and can be detected much easier. For this setup, you will need a balloon. Attach a weight to the balloon, for example, with a hook through the mouthpiece.
Looks like he's using just a
Create a wire loop
safety
to hold the
pin
balloon
or whatever.
and attach it to a stand.
Paperclip.
On the floor, you should place a metal plate to increase the volume of the impact and to protect the floor if necessary. And of course, you will need a needle to pop the balloon.
Do you see his face?
We will repeat this experiment
like,
a few times
needle.
for different heights. The resulting times should be the root of 2 times the drop height divided by the Earth's acceleration, which is 9.81 meter per square second. So for example, a drop from 1.2 meters should take about half a second.
Really simple equation. Very easy. And now he's just testing it at a bunch of different heights, which you will have to do.
As you can
There's his
see,
data.
our results match the theory quite well. But keep in mind that there are a few sources for errors. No sound rises instantaneously.
So his data points almost exactly match what he had calculated using the equation. And then he graphed that equation as a graph. So they are very well matched.
Above the threshold set in the app. So the different sounds of the popping balloon and the impact might have a slightly different delay when triggering the stopwatch. Also, the placement of the phone is important, as the speed of sound delays both sound events. Finally, there is a small delay between the ripping of the balloon, which produces the popping sound, and the actual collapse of the balloon, which initiates the drop. These are small errors, but they will prevent you from getting an exact match with the theory.
Those were errors. An example of what you should put in your report. I always like that part.
That's it for today. If you want to learn about more smartphone experiments, check out.
Okay, we're done with that. Yes, great. Wonderful. Okay, so we saw the funny little German doing all his cool little sciencey, fancy things. That's similar to what we're doing. It's not exact, but I wanted you guys to get an idea of what you'll sort of be doing or what you'll be expecting. It's the same concept. He did free fall acceleration. You can do this at your house. If you don't have the materials that he had and you want to do something different than what the lab says to do, be creative. Make up your own stuff. If you have, like, I don't know, a big long stick and you have like a step ladder, you have balloons at your house, or whatever you want to do. It doesn't have to be a balloon. Be creative if you want to. Just make sure that if you do try to be creative, note that in the lab and make sure that you say, hey, this is differentiated from, or this is different from the original lab because I did this and this and this, blah, blah, blah. Okay, moving on. So this is the equation that you'll probably be using. No, you'll definitely be using this equation. This is the motion during free fall of an object. So what is delta x? What does delta x mean? We'll break apart this equation because it looks a little scary. This equation looks a little scary. Right, it's the change in position or the displacement. It is the displacement between, well, you know. probably want to put that in centimeters or meters. Don't forget those units. Oh, there it is. Okay. VI, that is initial velocity. And it looks kind of funny here because the I is like super big for some reason. But this is initial velocity, which initial velocity generally, as we've seen in the homework, is equal to, generally, not all the time, but just generally. Yep, it's equal to 0, exactly. So probably this part right here will just cancel out and it will be equal to 0 because anything times 0 is 0. So moving on, you're gonna, whatever that is, it's gonna be added to 1/2 AT squared. That is 1/2 acceleration times time squared. So it'll look like in units, 1/2 meters per second squared times time squared. Cancel out. Sorry, second squared. Yes. Did I say that? Oh, yes. It's second squared. Meters per second squared times second squared. Cool. A, in this case, you can either use A or you can put G there because A is technically G in this situation, for sure. If you watch New Girl, this is funny. Gravity got the best of her. It's all over her white dress. That's a tragedy. Oof. Anyway, moving on. Things to know for the lab. So let's go ahead. Who has not read the lab yet? I know it was posted. I think Dr. Diamond posted it yesterday, I want to say. I hope. We'll go ahead and check that out. So we'll go ahead and move along here. Water. Whew. Okay. Okay, can you guys see that? I hope you can see that. Okay. There's going to be 4 parts to this lab. Part 1 is going to be kind of like an intro. It's going to be kind of like a pre-lab. We're going to check. It's really cool. I actually am really excited about part 1. This is a nerd talking, but it's really cool. So you're going to go on your Firefox app. You're going to select the acceleration with G. That is, one sec. That is right here. So right here. Which all of you ladies are very intelligent, so you could figure it out very easily. Particularly, you're going to use the simple section. I think that's part 1. Yes, part 1, yes. We're going to measure. The coolest thing about this lab, or this part of the lab, is we are going to measure gravity at your house or wherever you are at the time you perform this experiment. It's cool. You're going to see that gravity is not necessarily 9.81 meters per second squared. Not all the time. At my house, right here, I got 9.80079 meters per second squared. So technically, if you would do all the sig figs and all the fancy stuff, it's 9.80 meters per second squared at my house. That's what gravity is. Now, if we were in Colorado, it might be different. Depends on altitude. It depends on, yeah, pretty much that. So go ahead. Actually, don't go ahead and do that. You can do that on your later time, but I will show you the website just to show you. It's really old, guys. This website was probably made in the 90s. Yeah, by some old men that have no creative ability, you know. Okay, so yeah, so you just enter your latitude. This is my latitude. You enter your longitude. That's my longitude. And then you enter your sea level. So I didn't know the exact sea level, so I went to the Compass app, which if you have an iPhone, you will have this Compass app. And we've done this before. We've used this Compass a few times. So elevation at my house right now is about 300 feet. just look on there. Not sure if the latitude, so it also shows latitude and longitude. Not sure if you don't have an iPhone, I'm not sure if the Google Store or Google Play Store, I always get that confused, has that exact style. Like, I'm not sure if it measures latitude and longitude or measures sea level. Not sure. But just if you can't find it, just guess. Look up on Wikipedia or Google and just say, what is the sea level for Baltimore, Maryland? You know, if you live in Baltimore, make sure it's your exact city because it could be different. Okay, so this is what that looks like. Going back to the lab, set your phone on a flat surface and record the value the sensor provides for the absolute acceleration due to gravity. Make sure it's on a flat surface. If it's a little wonky, try to fix that, or find like a sidewalk somewhere that's level. So you can calculate the expected value of gravity using that website. So go ahead and just use that website to find this, part. Measured value of gravity would be your calculation. And you can also find, as with every calculation, there are errors. There are errors on that website. Nothing is perfect. There's always errors. Find uncertainty. I sent out an announcement last week that was about finding uncertainty of measurements. So go ahead and use that. If you want to do percent error based on both of those things, I think you actually do that down here in part 3. But if you just want to do it again, you can check yourself. Do it right here, and I would be happy. Moving on to part 2. Observe the accelerometer response when your phone is in free fall using acceleration with gravity. Firefox, on Firefox. So you're going to drop your phone. You're going to drop your phone into your other hand, which hopefully, let's see if this works. Okay, I did it. I am my hair color. I break things. This is why I can't have nice things. This is why we can't have glass cups in my house or china, because I will break it. I'm super klutzy. Yes, so please be careful. If you're anything like me, be very careful. I am personally not responsible if you damage an object or a phone in your house. I am not responsible for that. You need to use common sense to figure out what you need to do. I would recommend doing this experiment, preferably over a couch. Like, stand over your couch. If your couch is right here at the back, stand over it. So if it does fall, it will fall onto your cushioned couch. Or stack blankets. If you don't have a couch, stack blankets on the floor. Make it a big area because guess what? Phones bounce. And sometimes they shatter. So, and I put that disclaimer right here. I'm not responsible. I will not pay for your phone. This is on you. Good. Allow the phone to be in free fall for 20 to 30 centimeters. Now it's going to be really hard to judge, 20 to 30 centimeters. So make sure you have a good idea of what 20 to 30 centimeters looks like and make sure that that's where you put your phone. Cool. Drop it on different axes. You found the XYZ axis on your phone. If you want to drop your phone like this, if you want to drop your phone like this, if you want to drop your phone like this or whatever, make sure you note that. Put that in there. Explain or just write down what axis you used, preferably more than one. Include a screenshot of your data or a diagram if you like to draw. That's cool. Yeah, so that illustrates the response of 3 accelerometer sensors during free fall. Cool. Which is just the XYZ axis. Yeah. Part 3. Measure the free fall time for a displacement of about 1 meter. So if you don't know, this little squiggly line right here, that means about. It's about 1 meter. And we use that a lot in mathematics. I know engineers may use this. Physicists don't really use about unless they're estimating something. Okay, anyway, we'll get into this. go ahead and read over it, just like skim through it. Like I said, soft surface, mattress, do it over your bed, do it over your couch, get some blankets, whatever you want. Said doesn't need to be exactly 1 meter. However, whatever distance you measured, and it will tell you on your app, calculate uncertainty for it. It will have uncertainty. Uncertainty is error. Everything has error. You're gonna wanna practice this a couple times. I had to practice it quite a few times, but it's just about how quick you are. It takes practice, it's okay. Needs to be very accurate. You're gonna fill out a chart. You're gonna do 3 trials, like real trials. So you can try it multiple times, like way more, but you're gonna do 3 experimental trials. I want to see the data for that. All you gotta do is fill out the table. Then you're gonna determine the average value that you received from your data of gravity. Then you're gonna do calculate percent error. Cool. Calculating percent error. You already found up here in part 1 what the expected value of G was at your place of experiment. You know, whether you do it at your house, your mom's house, your grandpa's house, you know, whatever. Cool. Make sure if you change houses, if you do these things in different spots, you need to recalculate the gravity, the expected value of gravity wherever you do. You might need to do it a couple times if you decide to move. I'd recommend just staying at your house or staying at the same place. Cool. Part 4, determine the value of acceleration due to gravity graphically. So get out those Excel skills. And if you don't have them, go watch that video from Lab 2. It's in the modules tab. And it's in the Lab 2 description. It's down here. Watch that. You're gonna observe the free fall times for a variety of distances. So I'm gonna let you guys figure that out. I want it between 0.2 meters and 1.5 meters. So at least 3 different heights. I would recommend doing 5, but 3 minimum. So maybe like 0.2, 0.75, 1.5. There's 3 heights right there. Make them different enough from each other. If you decide to do 0.2, 0.3, and 0.4, I'm going to be a very unhappy professor. Okay. Your data won't be different enough for me to know, and it just shows that you're basically lazy, which all of you attending today are not, so good for you guys. Yes, you're gonna do a whole bunch of stuff. We're gonna get there. Going back here. You already know about this. Make sure, I think I said it should be in the simple mode for part 1. Yeah. I'm sorry, we keep using Firefox. I'm so sorry. I hope you get used to it. Okay, part 2. This is the stuff for it. This is probably what your graph's gonna look like when you first perform the lab. What we're gonna do is we're gonna zoom in on just this part right here. And it's going to be this, it's going to look like this. So this is the zoomed in version right here of this sector of the original graph. This is the zoomed in version. And see how it's like, let's see, positive 50, 0, and negative 50 acceleration. Cool, meters per second, sorry. Here's time. As we can see here, this is about 3.8 to 4.2 seconds right around here in the original plot. Make sure you check, double check to see if they make sense, to see if the time matches. Good. Your phone is dropped so that the velocity vector is along the negative z-axis. Does that make sense? Okay. Oops. When your phone is in free fall, so when it's in free fall, as we know, the acceleration is going to be 0. Your phone is going to measure that acceleration as 0. You should get a straight line on that 0, on the 0 line. It should be a straight line right there. It won't be when it hits. So right here is when it hits a surface. Okay. What you're going to do is you're going to take that data that you received and you're going to go to zoom in, okay? You're going to go to this pick data thing, which I have mentioned. It's highlighted in red right here. And that is how you're going to find this right here. Look, 9.84. Cool. And then you're going to do that same thing for the endpoint. So you're going to do it at the right as it starts falling, and then you're going to do it right as it hits the surface. Find those points. This is the earliest data point, last data point. Cool. I'm sorry, guys. I know this is boring stuff. I'm sorry. Yes, so, and here's a formal thing. Measure free fall time from earliest data point prior to the sensor indicating a change in acceleration due to free fall. I put a parentheses 3 here. We're looking at this part. So this part up is for this. To the last data point before acceleration due to the impact on the surface. That's looking right here. It's that point. I tried to put the parentheses 4 here to mean that this is the 4th image it's referring to. This is the 3rd image it's referring to, if you get confused. Cool. I also want to see this type of graph. So what you're going to do is you're going to turn your phone horizontally. And then you'll get to see that zoomed in. Fun, fun. Kind of looks like this. It kind of looks like that. Kind of looks like this right here. Cool. Very similar to what we just saw on the PowerPoint. Cool. Oh wait, what did Winston say here? Yes. I don't remember doing this. You won't either. What we're trying to do here is basically make sure you kind of understand conceptually what free fall acceleration is. You know, you're probably not going to remember all this graphing and all the blah, blah, blah stuff that you see. We want you to figure out, how do you calculate gravity? How do you find it? What is free fall acceleration? Just know that. I'm sorry, my dog's barking. Okay. In part 3, you know, as I said, there is a table that you have to fill out. On the lab, of course, you can see, we'll go back to that. And I'm really sorry about this. But Canvas, being as it is, did not let me put lines here. So there should be a line like right here, and a line right here, and a line right here, and here, and here. And there should be lines horizontally going like this, and this, and this. Please include that in your reports. Canvas wouldn't let me put those lines in there. If you don't put the lines in, I am going to be an unhappy professor. Like, this is, don't copy and paste this. Make your own table, okay? Make your own. Good. What else? Write down measured value of G. Do that. It asks for it. And it also asks you to calculate percent error. Don't forget to do that. Please, please. Error is so important in science, in anything. Especially if there's quite a few people that are going into pharmaceuticals, or like pharmacy, pharmacists, pharmacy techs. Error is very important because if you get a milligram wrong, it could mean life or death for somebody. So if you're filling a vial of liquid, there's going to be error there. Try to minimize that error as much as you can. There will always be error, but big errors are not good. You might kill someone. Okay. Graphs. More graphs. This is for part 4. Did we go over part 4? I don't remember going over part 4. I don't remember. We're gonna bring that over here. We'll go over it again. Cool. So this is where you're gonna do a whole bunch of graphs. You're gonna make a whole bunch of them. Really, you're not. It's only gonna be like 3 graphs. I put a lot of graphs in the PowerPoint. This is just giving you an idea. I don't wanna like see this, like just screenshot it, or, you know, you don't need to include, let's see, how many did I include? 1, 2, 3, 4, 5, 6. I don't wanna see 6 graphs because I zoomed in on the data, which then therefore made another graph. So I don't need to see the zoomed in version. Create a data table. You know how to create tables. You're gonna create a graph. It's gonna be a height versus free fall time. So remember I said that the time of free fall, that acceleration should be 0 for that on your Firefox app. However, acceleration is not 0 because we're not calculating acceleration going like, you know, of your phone. We're calculating free fall acceleration. So it won't be 0, but it will look like 0 on your phone. Cool. You're gonna also graph the height versus the square of free fall time. We'll look at those graphs and see what they look like. You're gonna also include a best fit for that data. If you don't know how to do it, I recommend typing in Google, how to find best fit of data in Excel. That's your responsibility to do that. Determine gravity from that slope, from that best fit line. Include that graph in your report, of course. Okay, great. Moving on. Ugh. Okay, this one. All right, as I said, this is the zoomed in data right here. I'd rather see the zoomed in data than the, so I'd rather see your zoomed in data so that way I can make sure that it's accurate. You don't need to give me this unless you want to. It's really just zooming in, really just scrolling. If you want to include that, I'm not gonna take off points, you know, it's no big deal. But, you know, okay. This is the table that you need to make. It says create a data table for your data and include it in your report. Data table. As you can see, whatever heights you do, list those different heights. You can do, the minimum is 3. I would recommend doing at least 4 or 5 heights. This guy did 5 heights. And then you'll be able to really tell and really be able to differentiate between the times of free fall, for sure. Yeah, that's that graph. The next one is going to be on free fall. Oh, I have to, whoops, got to delete that. Okay, so this is the best fit line right here for the height versus free fall time squared. And there's a calculation here that they did. And I screenshotted this from Excel, or yes, Excel. So I accidentally put this thing right here, which I will zoom in so you'll be able to see it better. Yeah, so I'm sorry about this thing right here. But it basically says 9.91 meters per second squared, which is the gravity that they calculated. This is the formula. Oh, and D equals, yes, what's up?
Professor, so for the free fall square, that means you just have to square the value that you measure, the first one?
Yep, you just square the times. So basically you're squaring these numbers right here.
So you don't need to do separate data for the free fall time square versus height.
No, so yeah, so this is the original one, and then for the squared, you'll have a different table, of course, and then that graph will be of that. So you have to first calculate free fall time squared. So you need to square these times.
Okay.
Which, one second. I just want to double check that this data is correct. Okay, it is correct. Okay, gotcha. Yeah, that weird number looked a little weird. Okay, yeah, so basically you're just taking these seconds, and you're squaring them and then creating another graph for that, table and graph. Make sure to include the table as well. And then find the best fit for this particular free fall time squared. And then D right here, what is D?
Distance.
Distance. It's X. It's really just X. And let me see. This is so weird. Ooh, okay. As I said back in where was it? Back here, as I said before, this would cancel out because your initial velocity should be 0. Time should be 0 when you're first doing it. So time at the initial is 0. So these would cancel out. And we're looking at basically, this is D equals 1/2 GT squared. So that is what they're doing for this plot right here, this graph right here. The slope, you'll find the value of the slope, which is y equals whatever you get x minus error. You're going to take A and you're going to find A. You're finding the acceleration. So you need to find acceleration using this graph, or sorry, using this equation. Cancel things out, you know how to do it. A equals whatever 2 times the slope, and the slope is right here. Just letting you know. And then you'll find your acceleration from that. Cool. This is for the distance. So this is an example. If I chose 1 meter, this would be what your graph should look like, or about what it should look like. So this is just giving you an idea. If I go over here, we'll give you another idea of what other measurements will look like. So this is for 0.8 meters. This is for 0.4 meters. So it's going to look a little different. It's going to look a little bit different from this as your height decreases. So as you get smaller and smaller heights. Like this is 0.2 meters. Yeah. So it's going to look a little weird, a little different. Wait, crap. Can you see that? Okay. Cool. Good stuff. Okay. Questions or comments? Can't believe I did that in an hour. Any questions or comments? Which, of course, these stupid things. Okay. Do you have any questions about the lab or about how to do a particular thing, how to configure your Firefox? I feel like you guys should kind of be a little more familiar with Firefox by now. It's, it's been like 3 weeks and we've used Firefox, which, I'm sorry. It would be a lot more fun, like in class, like we'd use like a bunch of different physics instruments and it would be so awesome. But unfortunately we have this and everybody has a smartphone, so we're kind of limited. Did we meet Friday for the last time? Yeah, so I had office hours last Friday for like 2.5 hours. And I was like, hey, I'm gonna mute myself because I'm talking to my fiance, blah, blah, blah. But if you have a question, just say, hey, Professor Smith. And I'll be like, yeah, because I have my sound turned on. And I will unmute myself and then I will answer whatever questions you have. Even if it's the tiniest little question, like, does this graph look okay? I'm here, that's what I'm here for. I did that on Friday. I wanted to test it out and see how you liked it. I think we only had 3 students that came to that, or 4, no, we had like 4 or 5, but they were like in and out, of course. You know, Friday nights are usually busy. It's COVID. I figured to be a little less busy, hopefully, not going out and going to the bars. You know, please don't. I care about your well-being, okay? So please stay home. So that's why I did Friday. And Friday evening, because if people do have to work, I did 4:30 to 7 o'clock. And that seemed to be okay. I might do it a little later this time because I had an event at my house at 7 o'clock. So I had to leave a little, you know, at 7, but I could probably go to like 9 o'clock. I know people have a lot of questions. It's up to you. So do you think I should keep it office hours on Friday, or do you think I should continue to do it on Wednesday at 11 o'clock in the morning? What would you prefer?
Either one works for me.
Okay, that's good.
It's weird because like I was waiting for like an announcement, but like, I don't know, I'm like all over the place sometimes. So I guess I missed the office hours on Friday, but I was expecting them, but I guess I didn't see them. I don't know.
Okay, I did post them in the announcements.
Yeah.
It's like, hey, it's moved to Friday. Woo. Okay, will do. Keep office hours on Friday. Will do. Okay, I'll change that in the introduction page. It's a video, the introduction page, which I don't even know if you guys went to. It's a page where it says start here, and it's like a picture of Dr. Diamond and his video. You click on his video and read it, and then it has all of his information below his video, and then you have my video and all my information below that. So I will change it there, and probably I will try to send out an announcement the day before, and then I'll send out an announcement right before I have office hours. So I hope that's okay. Is everybody good? Nobody has any questions? All right. Sounds good. I hope you guys have a great week. As I've said before, I am here for you guys. If you have any questions, whether you think they're stupid or not, as long as they're not stupid on purpose, I'm here. I'll answer them. You know, I gotcha. That's what I'm here for.